And without further ado, that's me. That's my mustache. I don't have the sunglasses today though, but I mean, hopefully everyone sees and understands that that's me. My take today is to take you through a bit of a storytelling around federated learning, and it is based on, hopefully by the end, talking about some of the research that has been happening within the federated learning space. I hope to kind of show a bit more theoretical side of things rather than the extreme practical things, and yeah, that's my take. There will be a bit start on the business side of things, like why is it important and why is it cool, and then at the end there will be a nice flow diagram taking you step by step of what the guys have been doing from the research paper mentioned. So, to begin with, the secret lies of your devices. As you can see in the image here, any device that you have, whether it's your phone, whether it's your Fitbit, or telling you about the Strava records and everything else, or your Oura Ring telling you about your emotional state today, everything collects data. A lot of these companies then will send this data privately to their big servers and try to build their machine learning models. But then the question begins with, what if we had those AI models on our devices, rather than having them working only centrally? Why about if you have small devices, small tiny models running on your actual devices? So this is the kind of trajectory of this topic. And the story begins here with Singapore shipyards, predominantly because Singapore is one of the biggest logistical centers for containers and managing any kind of containers going through Southeast Asia. And one of their companies recently called Tuas Pos, they are building in 2022 towards 2040 plan to process around 60 million containers, and a lot of that is or planned already to be managed and utilized by autonomous guided vehicles. So kind of like Amazon warehouse, where you have a ton of little vehicles managing these big containers, but no AI labeling. Maybe something like Merck and everything else, which is insane if you think about it. 65 million containers by 2040 is quite a big task. So of course, although they are automated, you can envisage they will probably have some AI models running on them because everyone likes AI nowadays. And so therefore, the question begins to ask, is it viable to actually have AI models running only centrally? So this is where it leads us before to federated, privacy and security. So before I go around federated learning, I'll go a bit about fundamentals of what privacy and security means, because sometimes you can't have privacy without security, but you can have security without privacy. A little example here is if you have a house with a little bed, no wall, no windows, you have no privacy nor security. But if you actually put some windows on the wall, you'll have some sort of security, but no privacy because everyone can still see through. And once we add some curtains, therefore nobody can see stuff. If it was technically a technological point of view, you can have HTTPS encrypting all of your data transfers and everything, but your internet provider will still know where that information went or who did you try to communicate with. So therefore, security is good, but the privacy, questionable. And then, going forward with that, what is federated learning? The neighborhood watchers like to say. Technically, as some people here in the audience will understand, federated learning is similar to distilled learning or teacher-student model, where essentially you will have a group of models that try to share information between one another to actually train together. So rather than you having one centralized model sometimes train everything one by one, you'll have a group of them together, training and learning, and then sharing it with the teacher or sharing it among themselves. The reason for that is that sometimes you want the models to actually work locally, to process their data privately, and not actually send anything across. The only thing that they wanted to send across is either gradients or the parameters of the model. And sometimes we realize that actually was not the best idea, because if you're keen enough and interested enough, you can utilize that data to actually get back the training models or the training data that was used to that. And you can devise, and some people did that. So before we jump to the research paper itself, I will tell you about how the federated learning model worked, or the two cases. So one of them is through centralized server, where essentially you had the one mothership that would essentially train itself on everything and then distribute that to little local clients. Those little local clients will train with the local data. They kind of get new ideas and new kind of parameters and weights and everything, and then they will send it back to the central kind of mothership that will actually try to aggregate all of that knowledge and information and send it back. So this is the centralized workflow. Why it works is because it is useful, for example, let's say if you're a central bank, you don't want to share any information. If you're a hospital, you don't want to share any information with everyone else. You're more likely than not to say, I am the controller, I want to do everything myself, and I don't want to share it with everyone, but I'll send it to the clients on the side. And that's what basically happens here. Sometimes it's good for central control because everyone nowadays talks about the single source of truth, the centralized data sets, the centralized control, and it gets a bit boring. But then you also have distributed training workflows where it is peer-to-peer. In this case scenario, you actually have models where they'll distribute it across the peers. The peers will train with their local data, and then they will share the parameters across each other, whether they like it or not, multiple times. And then there is no centralized governed body, but it is useful because in this case scenarios, for example, let's say if we have a lot of central banks working across different countries and they do a lot of fraud detection, they're actually trying to utilize that information to understand how to work better together. And sometimes it's good because then maybe it will be more beneficial than only one central bank understanding in one country how they will operate and work. If there's anyone in the financial sector working here, please let me know because I'm curious to learn more. How do you actually utilize AI within your services? Because that's quite cool. And any questions so far? Nope? All right. So, why tiny models? The agile agent advantage. As you can see in the image itself, you have a little guy kind of looking like Wall-E. This is our tiny model. And then there's a bigger guy, like a big LLM that everyone's used to nowadays, like GPT and everyone else, to actually tell it what to do. The tiny models, they require far less resources. So of course, all of your devices are not the most optimal running devices. You know, they still have their limits. How much RAM they use, the network they can handle, and everything else. And this is where tiny models, like for example, would say Bloom and stuff, would be actually far more beneficial to run locally because also it reduces the latency of decisions and the inference that takes time. Because now, for example, if you text, let's say Gemini, GPT, Claude, whatever it may be, even now it will take you 4 or 5 seconds. And if your phone or a crane tries to handle something which is very important in very real time, it will not be as good. So this is why the tiny models can be sometimes far more important and useful than having a big LLM model running on your local device. Having said that, if you take time to actually scan this QR code, you'll find the research paper I'll talk about the next 2 minutes. Thank you. I'll let some people scan it. Oh, nice to see a few keen eyes. And while you guys are scanning that, so the actual paper is based on an open resource project called FED, Federated Learning. It is based by a group in Hong Kong and China. And they have a few cool projects running at the moment, but one of them is about improving the learning algorithms between the models. And in this case scenario, federated learning was practiced between heterogeneous system, meaning that your main server, as I was showing here, for example, your main server at the right-hand side, the orange one, is actually a big LLM model, while the blue ones are actually tiny models, like for example, Bloom and any other lower spec model. And the problem with that is that sometimes when they do want to share information, they cannot do so because A, they're designed differently, they have different setups, they have different tokenizers used, so therefore when you try to mix the information among them together, it becomes quite difficult to actually make sense of it. So what these guys came up with is a process where essentially you have a client trained locally on the private data, of course, kind of like federated learning, but with a few more steps. In the first one, they train on private data using parameter-enhanced fine-tuning, in this case specifically LoRa, only because they actually want to go into deeper weeds in the bones of the model training rather than using something like prompt tuning. And then after the client is done training on that, they will try to compute the lodges on the public data. So rather than sending weights or the gradients, they decided to send an opinion of a specific answer based off the public data, because they don't want to send gradients and weights, because again, you can use like diffusion models to actually revert anything back and find out more answers about that. So that's why they try to utilize the logits. Once they upload those logits to the HQ, they do something called token alignment, and that was devised around 2-3 years ago, where essentially they said, again, as I mentioned earlier, if you have two different models having two different tokenizers, you actually have to create a common language between them. So that, for example, let's say if you have two people speaking foreign language, they speak two different languages, they can still agree on some documentation or something else in terms of opinion to actually make sense of it together without having to understand each other. So in this case scenario, what they did is they mapped the two actual tokenizers and they actually tried to create their own mapping dictionary. So that essentially they actually understand how to mix the two processed words from one model to the other. And once they do that, they actually send all of that information to the server side. As it goes to the server side, they have another thing where they let the server to decide whether the logits that the client has sent make sense to them or not. And they do that on cross-entropy losses to understand if the losses from the client side are lower than the server. If they are, then they take them in and they say, yes, it's good. If not, then they cancel it and they ignore it completely. So then your server is not just taking in everything that your client sent. It actually has time to actually think about it and decide and make a decision. What's the best information for them? And it's purely about the opinion. There is no data, there is nothing like parameters and gradients again. So pure understanding. Of course, can have its downfalls because you can say that you have a client that actually faulty and actually kind of like a misbehaving client on purpose to actually feed false misinformation logits. But it is something that paper has addressed as a limitation and hasn't considered how they're going to deal with it yet. Once it comes to the server side does very similar thing where it trains on the public data, it understands its logits, it aggregates and learns, and then sends back any kind of most meaningful logits back to the client side. And so what this means is essentially it picks up the best information that it needs about any of the client side things, and then distributes to all the other clients so that everyone has kind of a shared understanding of the system. Any questions? No? Cool. So this cycle can repeat multiple times. The models can speak to each other through the central hub, and because the client side is a little device in this case scenario, it can do this multiple times, but of course it can come with its own downfalls. And it's very similar to distilled model training. The only difference here is that they try to address the issue of being heterogeneous, so different models on different devices. Because in reality, if you're in production state, if you have a company or system with thousands of these devices, more likely than not, they'll be using different models. And so therefore the question becomes, how do you deal with the issue that, you know, different models learn differently and you want to make them communicate? And so deploying the SLM at the edge, beyond the shipyard or beyond anywhere else. The issues with these things is that practicality becomes a question. So for example, if you have 1,000 devices, you have 1,000 of issues. First is to orchestrate them. Second is to deal with the bandwidth and all of the kind of data that actually has to travel back to the central server, which becomes an issue. And also, if some of these devices actually go offline, that means that your server is getting less information from some of the models running online at the moment because they're completely dead. So therefore, you have to mitigate for those risks as well and those difficulties. But it also means that technically, if you do make it live and possible, then you shouldn't worry about all the multiple devices that could be running potentially your AI model. And for example, your phone, your Ring, your Fitbit doesn't actually have to send everything back to, let's say, Google central server. It can operate on its own local data online, locally for your phone, anywhere else, without having to deal with the issue of privacy and security. And yes, that's kind of my end of the talk. If anyone has any questions, please let me know. But also, please reach out to our dear Rachel O'Keefe, our talent partner, who is happy to talk to you about any jobs that we have at the moment, and any of our members of staff across the room. Please wave everybody, and another QR code. Thank you.